Good morning, 380. This is part either 3 or 4. I think it's part 4 now. Want to talk one more little brief part about standard scores. They allow us to make meaningful comparisons between sets of scores that have different measurement units. I do want to say that z-scores and t-scores, you have to have the mean and standard deviation calculated in the formula. I will give you the mean and standard deviation, and then you would have to calculate the resulting z-score and the resulting t-score. For example, with z, you would take an individual score, subtract it from the mean, and then place it over the standard deviation as a fraction. So it's x minus x bar over s for standard deviation. Now t, again, it gets rid of the negative numbers, and so again it runs on a mean of 50 and a standard deviation of 10, so it would go from 20 to 80. 20, 30, 40, 50, 60, 70, 80. And the formula basically is 10z plus 50. Again, the 10 stands for the standard deviation unit, 50 is the mean. And so those are the last points I want to make about standard scores. Now, correlation and subsequently regression, although we won't spend too much time on regression. Correlation involves two different variables. A lot of times coaches, teachers, researchers, we want to look at the degree of relationship between two different variables. So, for example, what's the relationship between the bench press and the leg press when I do different tests? What do those tests have in common? And so to measure that relationship, you would do something called the coefficient correlation. In this case, it would be Pearson, and in some other ones, it would be another name for if you have ranks. So correlation allows you to determine a linear relationship. Now again, linear is a straight line, and so the two variables, it tries to predict the relationship in two different ways: the magnitude and the direction of the relationship. And so the association that's perfect, either a +1 or a -1, will be a perfect straight line. In other words, as x goes up, y will also go up a certain amount. And the perfect correlation graph, if I graph a perfect correlation at either -1 or +1, it would be a straight line. There'd be no variance. It'd be a perfectly straight line drawn, and the angle, of course, is determined later on. So again, the correlation has either a positive or negative direction, and the magnitude is between -1 and +1. And that's what I say by scale right here. When I say scale, it's actually the magnitude is +1 to -1. Now, the strength of the sign doesn't matter. And again, high and low is subjective, and it's obtained by many different things. There's nothing bad about a negative R. The sign simply indicates the R, how the two variables covary or go together and what they share as far as the variance. If you have a positive R, it indicates that people scoring above the mean on one variable, X, will usually be above the mean on the second variable, Y. Then, of course, a negative correlation indicates that those scoring above the mean on X will generally be below the mean on Y. Thus, a correlation of -0.5 is not the same as one of +0.5, but they are equal in strength, but opposite in the direction. Okay? And that is very important to know. So direction is not important in correlation. A -9 is as strong an indicator as +9. It simply means that one goes up as the other goes down, and a negative correlation is one goes down as the other goes up. I have a mistake here. One goes up as the other goes down. That's not right. Let's correct this. Let's correct this right now. This needs to be goes up, because it's a linear relationship. And so let's make sure that one is corrected. And now, of course, what are some problems with correlation? There's 2 or 3 main problems with correlation. First of all, it assumes a linear relationship in that as one variable goes up, the other one will go up also. What if your data is curvilinear? In other words, it's not a straight line. In fact, some data is similar to the normal curve. It goes up to about halfway through the graph, and then it starts going down. I think anxiety and performance is like that. We've talked about that in sports psychology. There reaches a point in any sport or any activity where there's an optimal level of arousal, and then after that it goes down. It affects performance. So correlation wouldn't be very good for that. You'd have a very low correlation for curvilinear data. So it assumes linear data. The other thing that happens is you can't show cause and effect with correlation. In other words, you can't prove that X causes Y other than to say they are related. So when you say, well, smoking is related to cancer, that's true, but you cannot say that smoking causes cancer, as long as some people who smoke, if they do not get cancer, then that defeats the premise of that. You can say that there is a lot of evidence, there is a very high statistical evidence that if you smoke, you will develop cancer, but it doesn't prove that smoking causes cancer. So that's that cause and effect piece that's a little bit different. Now, while you're in your book, it'd be nice to take a look at page 66, because there's some scattergrams that talk about the various correlations and how much they mean. As you can see there, if it's a high positive of 0.8 and above, it resembles more of a straight line, versus no relationship. It's just random scattered dots, looks like on a graph. And so 0 to 0.7 really are not very good for predicting at all, because you really have no basis for a good prediction until it gets closer to 0.9 or minus 0.9. Also in 66 it says 0.8 and above is a good correlation. I'd probably try to get to 0.9 or above would be good, because again, if you have a 0.9, now you can say, well, 81% of the variance can be explained. But if I only have 0.8, 0.8 times 0.8 is 64. That's barely 2/3 of the variance of the scores could be explained by the variable. And so that's called the coefficient of determination. The final point, the other final point about limitation is the effect of the variance on the range of the data on the magnitude of R. And you know, variables with larger variances or ranges tend to have a higher R than variables with restricted variances. So that's kind of beyond our scope of thinking. But you know, the effect of the variance or the range of the data will determine sometimes the magnitude of R. So how much of a range there is. If there's a very small range where you only have 2 or 3 scores, so it's not going to be much. I mean, between 8, 9, and 10, there might be a lot of scores that are 8, 9, and 10, but it's not going to be much variance because the scores are so close together. And so if the data is spread out, like between 3 and 20, there'll be more variance or range of the data, and so that'll affect the magnitude of the data, and that's related to the variance. And so that's basically what correlation is all about. We use it quite a bit in our field. Now, there's 2 types of correlation. There's Pearson product moment for interval and ratio data, as you see here. And there's also, if you use rank, if one of your data points is a ranking of the class, then you must use Spearman's row. And that's, if you have rank data, you have to use Spearman's row. And if you have interval or ratio data, you have to use Pearson. And that's one of the prime reasons we talk about the 4 types of measurement, the 4 levels of measurement that we have as it relates to correlation. So the last use of statistics that we'll talk about is what's called linear regression, which is a simple and multiple predictors of a variable. And the variable that you're trying to predict Y from the scores, from the scores of X. And that becomes a little more of an issue. And so this is nothing more than regression is trying to predict a line of regression that crosses the y-axis given X and given a couple other aspects as far as the mean of your data set and the standard deviation. And so this is somewhat an introduction, or about the only example of inferential statistics we will use. We're trying to predict y and maybe look at the differences between different groups, x1, x2, and x3, on other variables or with different variables or groups. And this is called t-test and ANOVAs. T-test is trying to find how two groups are different. ANOVAs looks at the analysis of variance between the different groups. Very quickly, let's talk about regression. And when you have the mean and standard deviation for two variables, and you also have a correlation, it's possible to predict the variable of y from the variable x. And this is called simple regression. And a simple regression is simply called a linear regression because you try to find the straight line that best fits the data from variable x and variable y. So if you look on page 71, you will see there's the first calculation. It's called y prime, and that's the predicted value of y. It equals a plus bx. A is the y-intercept, where it crosses the y-axis, and then b is the slope of the line, in other words, how high or low, and the angle of the line, and then x, of course, is a known value of x. And so there's two things you have to solve for there. You have to solve for a, and you have to solve for b. And down below, formula 311 is how you calculate the b, which is the slope, and that takes into account your correlation, and then the standard deviation of x, the standard deviation of y. In formula 312, you calculate the y-intercept by looking at the means of x and y, and then plugging in the slope that you calculated in the previous example. And so the formula there is, with two means and b thrown in as the slope. So from that, you can predict basically the correlation and where that's going to go. And again, the closer the correlation is to +1 or -1, the more accurate the prediction. That's the key point. And then the next couple pages talks about multiple correlations, where you have multiple groups. And so when you have more than one group, that's called multiple regression. And you're trying to predict several. And of course, there are computer programs that do this instantly for you and so on. The only other part we'll mention is trying to find level of significance between two different groups, between sets of scores probably from two different groups. And this is called a small t-test, or the test of significance, or the test between means of significant differences between two groups. And again, a lot of times with these, you're looking at the 95% level in your normal curve at one end or the other end of that. So sometimes they're two-tailed, sometimes they're one-tailed, but that's not really something you have to know very much about. Okay, so I would take it pretty easy reading the rest of this from page 75 on. And you're just trying to find significant differences between groups, and then trying to see if those significant differences are caused by whatever variable it is I may be manipulating in the research. And this is what we do in more advanced statistics and research. We give one group a placebo, another group gets a new treatment, and then we try to see how those groups have changed. Did one group change? Did the other remain the same? And was the change significant? And can we say the significance was caused by the treatment? And that's what you get into independent and dependent variables and so on. Okay? That's all we need to know from the Chapter 3 Statistics. And this is part 3 ending from Statistics in Lacy's text.